Hello everyone, my name is Yibo Huang. I'm now a postdoc associate in Rice University. It's my great honor to present our project, NDSOX, which aims at enabling an ultra-low latency and compatible PCIe interconnect for rack-scale communication. This work was done during my PhD study and is in collaboration with Intel. Today, high-speed rack-scale network is strongly demanded due to the widely deployment of disaggregation racks. The disaggregation rack decouples one rack into different network-attached resource pool, which improves the resource efficiency. On the other hand, the model compute and storage hardware, such as GPU, TPU, and persistent memory, are deployed in a rack, which makes the network become a potential bottleneck. As a result, in many disaggregation applications, such as key-value store, ultra-low latency and high throughput communication is expected between different resource pools. The lower the latency, the better. Therefore, the remote direct memory access, or RDMA, has been adopted due to its high performance by offloading the protocol stack into the hardware. However, the current RDMA is still not enough for rack-scale communication because they rely on heavily layered protocol stacks. Here shows the RDMA transport stack. We can find that there are two overheads on the data path. The first one is the inevitable protocol translation among different layers. For example, the stack has to do the conversion between the PCIe and network packets with a different MTU size. And the second overhead is the complex unique resource management. For example, the RDMA uses limited NIC memory to cache the memory mapping table and the connection context. This results in high latency under the cache miss. These two overheads lead to at least 1.6 microsecond delay for one round-trip transmission. So, how to get rid of this protocol translation and the complex unique resource management? Fortunately, the advanced high-speed PCIe interconnect open up new opportunities because it overcomes the above two major overheads. At a high level, it enables super-fast across-machine access by directly using the lossless PCIe fabric. Here shows the PCIe interconnect stack. We can see that the application can directly send out the packet over the PCIe protocol via the PCIe verbs and endpoints. And there is no translation between the PCIe bars and network protocol. At the same time, the complex unique resource management is naturally bypassed. And the typical PCIe interconnects include the CXL, CZ, and the PCIe non-transparent bridge. And we focus on using PCIe NTB in this paper. So, advanced PCIe interconnects can enable higher performance than RDMA. In particular, the PCIe interconnect provides the ultra-low latency, such as around 500 nanoseconds one-way latency with the PCIe NTB. To demonstrate this, we ran the ping-pong micro benchmark to compare the latency of RDMA and PCIe NTB. So you can see here, the PCIe NTB can achieve up to 5.6 times speed up compared to RDMA. Also, the PCIe interconnect can provide the high throughput by matching the rapid involvement of PCIe bandwidth. Besides, the PCIe interconnect allows the cache coherent remote memory access. So it's time to rethink the design of ultra-low latency and compatible rack-scale communication with advanced PCIe interconnect. So our vision is using the PCIe interconnect for high-speed rack-scale network. You can see here, the figure shows the in-rack network architecture with the PCIe and NTB fabric, where we use one PCIe cluster switch to do the memory address routing between the different PCIe domains. We use a PCIe endpoint as the end host to process the memory mapped IO request. So by this, we can enable the low latency and a lightweight PCIe interconnect for the rack scale communication. However, the native PCIe NTP lacks transparency support because it is originally designed for device sharing across independent PCIe domains. So let me bring a simple example where host 1 wants to write the message in buffer 1 into buffer 2 on host 2. First, in the control path, the NTP Apple issues a verbs command to set up a global NTP context instead of the connection abstraction, and rejects the NTP mapped memory. Once the context gets ready, it exchanges the context with the remote side to set up the NTP data path. Then it can post the memory mapped IO request in this case. Then in the data path, the NTP endpoints process MMIO request using address routing and launch the local NTP Apple to directly access remote memory by bypassing the remote CPU. So our goal is to make rack scale applications to be able to use PCI interconnect in a transparent manner while preserve the high performance. So in this talk, I present NTSOX, a lightweight and host network over PCI interconnect for rack scale applications to achieve this goal. With this interaction layer, any existing rack scale applications of socket can run with a minimal or no code modification. However, this is still hard due to three key changes. So the first one is how to process the mismatch in communication abstractions. And the second change is how to enable scalable NTP database for concurrent workloads. And the third change is how to ensure the performance isolation when sharing NTP transport resource among applications. I will explain how we solve these changes in next slides. Now, let me explain the key ideas for design the NTSOX. In NTSOX, we introduce a software interaction layer that virtualizes NTP transport resources for REST-scale applications. At high level, the NTSOX layer gets socket API calls from the Apple and process them by interacting with the user level NTP library and endpoint on behalf of the Apple. NTSOX adopts a microkernel architecture that separates the control plane from the data plane. It consists of three key components: NTSOX library, the Marnet, and the proxy. The runtime NTSOX library is located inside the application process and provides the compatible and performant socket abstraction. And the Marnet acts as the control plane component to perform the control path operations, such as the connection setup. And the proxy acts as the data plane component and virtualizes the global NTP transport resource in a lightweight manner, and then coordinate with the library to perform the first database operation. These three components communicate through the shared memory. So the first change is how to overcome the mismatch in communication abstractions. Many applications expect to use a compatible socket context. However, the native PCIe NTP only provides a low-level incompatible NTP context. That means we should bridge the gap between the socket and NTP context in a transparent and efficient manner. For example, the NTSOX intercepts the socket connector call from the Apple, which is used to set up a connection. However, the native NTP context can't understand and process the socket and address because the native NTP has a default assumption that the NTP endpoints are exclusively controlled by device driver to enable the device sharing. So it lacks the connection abstraction. So one possible attempt is to reuse the socket management of the OS kernel, but it is inefficient because it involves a log condition and the context switch between the kernel and the user space. So how do we solve this problem? So we propose a socket-like connection abstraction over NTP transport context in user level. The idea is leveraging the global user space measurement for virtual socket, IP, and ports. In particular, we use the anti-SOX library to intercept the socket API calls from the Apple and forward the serious parameters into the anti-SOX monitor. Then the monitor runs as independent control plane component to perform the virtual resource management, such as the virtual socket and IP port allocation. And it maintains the mapping relationship between the socket and NTP context. So by this, anti-SOX bridges the control path semantic gap. Besides efficient control path, anti-SOX proxy is also expected to provide a transparent data path with a minimal system overhead. In particular, when the Apple calls the write operation, the data should be synchronized between the Apple birth and the NTP birth. So a possible solution is to directly copy the data between these two births, but this is inefficient due to the memory copy overhead. So how to solve it? We observe that the opportunity from the fact that the applications and the proxy are processes in the same machine, so they can share the memory region. So we propose a transparent zero copy mechanism by remapping the application birth and the NTP birth into the same physical memory region using the proxy. And the second change is how to use anti-SOX proxy to enable scalable NTP data plane for concurrent workloads from a variant application. As mentioned earlier, since native NTP is only used exclusively by original device drivers, it lacks scalability consideration for processing the concurrent request. Meanwhile, the global NTP mapped memory is an important NTP transport resource, but the size is somewhat limited. So how do we balance the limited NTP resource sharing and the data plane scalability? So a strong man approach is to organize the whole NTP memory into one globally shared RAM buffer using lock. We take the data sender as an example. So we build the send RAM buffer over the local NTP mapped shared memory within the anti-SOX proxy. Then the proxy forwards the data to remote site by performing the memory mapped IO write with the send point in a log-free manner. Then the applications use a log to consistently append the data into the tier of the shared NTP RAM buffer. However, this method is inefficient because the use of logs sacrifices the scalability of the data plane. We also observe that the performance of a single CPU core is hard to keep up with the model PCIe bandwidth. So, based on this observation, we propose a code-driven partition abstraction to unlock the multiple scale-out performance for the database. At high level, the basic idea is to divide the globally NTP memory into multiple code-driven parallel units, and each unit is correlated one partition with one NTP RAM buffer. Each partition is responsible for a group of connections. Particularly, per connection shared memory queue is first used to transfer the data points between the application and the corresponding partition. Then, each partition will do log-free proactive packet forwarding from the shared memory queue to NTP RAM buffer. So by this, the proxy can enable the log-free NTP resource sharing while preserve the multiple scalability. And the third change is how to use anti-SOX proxy to ensure the performance isolation among the various applications. For example, application traffic can be classified into bandwidth-sensitive large flows, such as Apple 1, and latency-sensitive small flows, such as Apple 2. They shared the small partition 1. So with the coarse-grained data forwarding, the small flow will be easily blocked by a large flow within the same NTP RAM buffer. This causes a high latency for small flows. So how do we solve these problems? The idea is to tightly combine the per-flow message slicing mechanism with a fine-grained proactive forward in the proxy. In particular, from the perspective of sending data, we first cart the message into the fixed size data packet within the library. Then the packet in proxy will proactively forward the packet from the shared memory queue to NTP RAM buffer at a specific mini batch. In this way, we can mitigate the partition head of line blocking issue. Besides, we also propose the inter-partition connection scheduling. The basic idea is to isolate the bandwidth and the latency-sensitive flows into different partitions. For example, the partition in the proxy can be defined as a low priority, such as 1, and a high priority, such as 2. Then, bandwidth-sensitive flows are mapped to low priority partition 1, and the latency-sensitive flows are mapped to high priority partition 2. So, thanks to this, anti-SOCs can enable better load balance and performance isolation. We also have other performance optimizations for anti-SOCs. So if you have interest, please refer to our paper. So we built the anti-SOCs based on DBTK NTP driver, and we implemented all anti-SOCs components in C language, starting from the scratch. And our test bed consists of 2 servers equipped with the PCIe reference adapter by Intel and RDMA capable NICs. So one nice thing about the PCIe is that it provides ultra low latency, which is significantly valuable for latency sensitive applications. So we first measure the end-to-end median latency of a ping-pong micro benchmark with anti-SOCs and other communication stacks. This figure shows the latency comparison. So here, the x-axis is the payload size, and the y-axis is the latency in microseconds. And we can see that compared to Latency TCP and RDMA socket, anti-SOCs achieves dramatically better latency by up to the 20.4 times and 2.3 times respectively. And the extra latency between the anti-SOCs and native NTP is small and acceptable. And the multiple scalability is another important requirement of using the PCIe NTP. Since the bandwidth limits of the PCIe NTP and RDMA are different, we use the ratio between the application throughput and the bandwidth limit as a metric, call it saturation ratio. And this figure shows the relative throughput performance on the concurrent workloads. A number of concurrent client threads sends the message into the same server. We can see that compared to the libVMA and the Linux TCP, anti-SOCs achieves a better and stable multiple scalability. This gain is merely from the partition abstraction. Further, to verify the effect of anti-SOCs performance isolation, we use a larger flow as a background traffic and measure the CDF of latency for small flows with or without ultra partition isolation mechanism. We can see that anti-SOCs eliminate the head of line blocking issue due to the partition-based isolation. So what about the real-world application performance? To demonstrate this, we first use anti-SOCs to support the key value store without the code modification. Meanwhile, to measure the application performance benefits, we run various YCSP workloads on key value stores with a different communication stack, and we measure the end-to-end median latency. So you can see that the anti-SOCs achieve better latency by up to 24.5 times and 1.6 times compared to TCP and RDMA respectively. So to conclude this talk, this aggregation today requires high-speed rack scale communications. However, Existing solutions are insufficient due to the inevitable protocol translation and the complex unique resource management. Meanwhile, the ultra-low latency PCI interconnect bring a great potential without the protocol translation. So today, we introduce the anti-SOCs that enables the rack scale applications to be able to benefit from the ultra-low latency PCI interconnect in a transparent manner. We address the three key changes in both the data and the control piece and ensures that the anti-SOCs can outperform state-of-the-art solutions. So please check our paper and our GitHub repo for more details. And I'm happy to take any questions. Thank you.